In the last exercise, we considered what the membrane potential of a neuron would be if it were permeable to more than one ion species. It would be useful to have an equation that could tell us precisely what the membrane potential is expressed in terms of the ion concentration gradients and the relative permeabilities of the neuron to the different ion species. Such an equation exists. It is the Goldman-Hodgkin-Katz equation, and it states the following. It tells us that the membrane potential of a neuron equals RT over F times natural log, and these of course are the same terms that we see in the Nernst equation, so we can simplify this to 58 millivolts times the log base 10, and we take the log of this term here, which includes the ion concentration of potassium outside over inside, the sodium concentration outside over inside, and the chloride concentration inside over outside. And these concentration terms are multiplied by the permeabilities of the ions to the different species. So the potassium outside and inside is multiplied by the relative potassium permeability, and then sodium and chloride, and so on. I'd like to consider a few things about this equation. First, we see that the gradient for chloride is inverted with respect to that for sodium and potassium, and I'd like you to think about why this might be, and we can discuss this in class. Secondly, we see that this equation, the Goldman-Hodgkin-Katz equation, will simplify to the Nernst equation if a neuron is permeable to just one ion. So for instance, let's consider a neuron that's permeable only to potassium. That means that the permeabilities of sodium and chloride are 0, and therefore these terms here drop out, and we're left simply with this term telling us that the membrane potential equals 58 millivolts times the log base 10 of potassium out over potassium in, which of course is simply the Nernst equation for potassium. Now, these ion gradients are multiplied by the permeabilities of the different ions, and it's important to realize that the concept of permeability is related to, but not exactly the same as, conductance. We talked about the conductance of individual ion channels previously. This is related and tells us what the permeability of the membrane is to a particular ion species, but these two concepts are not exactly the same, permeability and conductance, and we can discuss in class what the difference between these two terms is. Now, when a neuron is permeable to more than one ion, we have what is called a steady state condition, and this differs from the equilibrium condition that we saw when a neuron was permeable only to a single ion. And the reason for the difference is the following. If a neuron is permeable, let's say, to both potassium and sodium, then the membrane potential will be somewhere between the potassium equilibrium potential and sodium equilibrium potential. Because we're not sitting at the equilibrium potentials for either of the ions, there'll be a continuous efflux of potassium from inside the cell to the outside, and at the same time there'll be a continuous influx of sodium from the outside to the inside. Now these two fluxes will be equal so that there'll be no net change in the membrane potential. The net charge flux across the cell will be 0. So we have a constant voltage, the steady state voltage. However, we have a continuous running down of the concentration gradients. Potassium is continuously running out of the cell, reducing the internal potassium concentration, and sodium is continually flowing into the cell, raising the internal sodium concentration. Thus, the ion concentration, the gradients are running down, and in order to maintain constant gradients, the sodium-potassium ATPase is activated, pumping sodium out and potassium into the cell. We will continue our discussion of the Goldman equation by considering an experiment that was done many decades ago. The Goldman equation tells us that the membrane potential of a neuron varies as a function of the ion gradients across the cell membrane. And in this experiment, the ion gradient for potassium was changed by systematically varying the extracellular potassium concentration. So this is shown in the graph on the left, where the membrane potential of a neuron is plotted as the extracellular potassium concentration is varied from a control level, a normal level of about 3 millimolar, up to 100 millimolar or even more. By raising the external potassium concentration, this changes the potassium gradient across the cell. It will change the potassium equilibrium potential, and as a result, it will change the resting membrane potential. The membrane potential, as the potassium concentration is varied, is shown in these points here, and it's fit by this curved line here. So it tells us that as the potassium concentration is varied, the membrane potential varies as well. The same experiment can be done on glial cells, where the membrane potential of a glial cell, shown in these open circles here, is plotted as a function of the extracellular potassium concentration. You can see that these two relations differ in a very important way, and the exercise considers these differences, and the three questions that we will be discussing in class are outlined here. So I'd like you to consider these, and we will discuss the answers in class.